Okay, another great day of of formal methods, and today your homework is due. You have a homework assignment due, and it's the first, I think, really substantial, substantive one. I mean, what we've been doing up to now has been kind of learning how to do the textual substitution, substituting equals for equals, and this one you had 7 exercises, and some of these were pretty tricky, and so I gave you some hints on the course webpage for these, and also the book. There were also some hints in the textbook. So when I assigned a proof, a proof to do, then if you notice, it said see the hint in exercise whatever, and that exercise is to do that proof, and then there's a few hints that our author gives you in the book. All right, so I anticipate that usually at this point in the course, after this homework assignment, there's usually lots and lots of questions. So, any questions?
Can we work out 347B?
Can we work out 3.47b? Okay, that was the very last one.
Yep.
That's De Morgan B.
Yep.
Well, did you see the hint?
Saw the hint.
So De Morgan B is to show that not P or Q, not parentheses P or Q, equivales not P and not Q. So that's De Morgan B. And I think the hint said to start with the left-hand side and to get it to the right-hand side, but it also gave you the first step on the left-hand side.
Yeah.
The left-hand side, it said pull a rabbit out of a hat, and instead of writing P, write not P, and instead of writing Q, write not Q.
Yep.
Yeah?
Yep.
So what's your question? So that was the hint. You don't know where to go from there?
No. I don't.
Okay. Oh, hold on. Shh. That's.
I didn't just say it. It says in the hint as well. Use De Morgan A.
Oh yeah, and use De Morgan
That's
A.
the next step.
That's the next step.
Use De Morgan A is the next step.
But the trick on this is to see. Yeah, the hint was to use De Morgan A. But the trick on this is to have the insight of what to use for textual substitution. I mean, because you have to use De Morgan A, but with what replaced by what? Now don't say it. But, okay. The trick is you need to use De Morgan A. But obviously, if you look at what you have, then what you have does not look like De Morgan A. So you've got to use De Morgan A. You have to get De Morgan A in a form that will look like what you have. Well, anytime you use a previously proved axiom or theorem, you are at liberty to have any one of the variables be replaced by any expression. So my question is, look at what you've done so far. How can you make what you have look like De Morgan A? It would be De Morgan A with PQ, don't say it, with PQ replaced by any expression, right? Now, was that enough of a hint?
Yeah, I suppose.
This is much as you're gonna get.
I mean, I'm surprised that you don't have a question about De Morgan A itself, because that was also assigned.
You gave us every single step, though.
Well,
yeah.
I suppose I did.
That was going a little bit far.
Maybe I should not have been so generous with the hints.
No, you should.
I should have. Did it still take a while to kind of see how to do the substitutions?
No.
No.
You literally gave us every step. And the substitutions. Just saying.
So,
All right. Let's see, we're missing
Ben and Mason.
Oh, right. Oh, Mason's,
Dead.
well, no, but has Yeah, he came by yesterday. He might not be here. Anyway,
Cool.
any more questions?
Yeah.
I can't believe that this is it.
You say we're a good class.
I did say you were a good class. No more questions about any of the other ones? Did you get them all now? Whoa, well, maybe we should just all go home. No, just kidding.
That'd be real.
I could go.
Actually, there is, I wanted to wait till everybody was here, but there is an announcement that I want to remind you about. It's on the syllabus, but we have a midterm exam in here on Thursday, right?
Really?
Yeah. So Thursday. That's 1 week, yeah.
We're just proving.
Yeah, I'll tell you more, as it gets closer to the, in the next lecture or two, we'll talk more about what's going to be on the test. And also, we can probably schedule a review session outside of class if you'd like,
No, thank you.
to go over some of this stuff. Okay, I have, I've got one more cartoon for you. Now, what does the golden rule do? You don't know what the golden rule does?
It changes from or to and.
Yes, the golden rule is what connects conjunction with disjunction. So now that we know about or and and,
I have a question.
oh, good, another question.
Just curiosity. If you had started with conjunction
Uh-huh,
and you'd done
all of that stuff,
all those theorems first, would the golden rule be?
it would probably be the same,
Well, yeah, but
only
it would be, and then you wouldn't.
you'd be defining or in terms of and instead of and in terms of or.
Exactly. So symmetry of or would be a theorem rather than.
Yeah, probably. You could probably do it that way. But on the other hand, or and aren't quite, there are some theorems up here that don't apply to and.
Like that one.
Like which one?
Zero.
I know. I tried to do De Morgan B the same way I did De Morgan A at first,
Yes.
and
It's
because
not pretty.
yeah, it's not.
Actually, you can do it. You can prove De Morgan B the same way you'd prove De Morgan A. That's actually possible.
Even though we don't have 3.32 for conjunctions,
Yes.
we use that one twice for.
Yes. Yeah, you can actually use 3.32 twice to prove De Morgan B without resorting to De Morgan A. It's actually possible.
Huh.
Substitution is just nasty.
Anyway, here's my cartoon. April 19th, 1906. The first insurance agent is tarred and feathered. You remember, you know your history about the San Francisco earthquake and fire. There was a big earthquake in San Francisco in 1906, actually, April 19th, There's a huge earthquake. It's a historic event. Huge earthquake, and because of the earthquake, the city caught on fire, and then after the earthquake, the whole city burned down. Practically the whole city of San Francisco. That's a historic fact. So anyway, here are these citizens of San Francisco, and here's an insurance agent, and he's saying, I'm afraid you overlooked the fine print. Your policy covers earthquake or fire, not earthquake and fire. So, but unfortunately, they could have a retort to this because if they interpret or the same way we interpret or, what does P or Q mean? It means
One of them has to be true.
P or Q or both. The insurance agent, is not using our definition of or, right? He's using the exclusive or definition. He's using the definition of or where it's this. P, Q. There's actually a symbol for the exclusive or. It's P plus with a circle around it. This is exclusive or.
That's not an
So it's the or, no, yeah, this is the symbol for exclusive or. And it's the way it works is like true, 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 false,
That's not
false,
on
true,
Preston's table.
false, false. No, we didn't put a symbol to this. But the way it works is if one or the other is true, it's true, but not both. So this is false, false. So how does this differ from, how does this differ from
The first one's true.
P or Q? P or Q would be what? True, 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 false. So see, they differ in this first row here. So anyway, a little humor. All right, well, if there's no other questions, then we will continue on to the next operator that we will investigate is going to be implies. Okay, so we have conjunction.
What's the homework for?
The homework, yeah, I will show you what the next homework is going to be. I have it noted here. It's oh, I'm sorry. Look at this. There is a symbol. Yeah, I was using the circuit. I was using the digital circuit symbol for exclusive OR. Actually, exclusive OR, I should have recognized this. The symbol for exclusive OR is not equivales.
What?
Not equivales is also called exclusive OR in computer circuitry. This is not equivales, right?
Yeah.
Because it's if they're not equal, it's true. Yeah.
You,
So I was mistaken. I had forgotten. I was
So
thinking about circuits instead of.
any operators that have the same truth table are interchangeable?
Yes. Yes. Of course, we're not dealing with truth tables anymore, but anyway, that is the case.
what was that?
And because I just saw, look, 3.53. It's called exclusive OR, and it's this. And what it is it's not P and Q or P and not Q. So this whole thing can only be true if one is true and the other one is false. If they're both true or they're both false, then they will not be. Then the result is false.
What was that one?
And here's equivalence. P equivales Q is P and Q or not P and not Q. Those all make sense. And you could prove those, although I'm not asking you to prove those. Okay, now the homework for next time is all about a new operator that we're going to define now. It's called implies. And we've already done the truth table for it. But here's how it's defined. It is defined by 3.57. Okay, so 3.57 says P implies Q. This is 3.57. P implies Q equivales P or Q equivales Q. That's the definition of implies. Yeah? So anytime you see an implies and you want to get it to something that went before and then you want to manipulate it and get it back, this is one way you could do it. You could replace this P implies Q to be P or Q equivales Q, and then you can manipulate and then you could get back. This is one way you could do that. So because this is and we will never ask you to prove 3.57 because 3.7 is a definition, which means the same thing as an axiom, right? Now, 3.58 is named consequence, and that just follows from, but that's pretty simple, right? P follows from Q equivales Q implies P, right? So we've seen that before. Now, here's a famous 3.59. Famous. I have actually had students come back to me like 2 or 3 years later, and they still remember 3.59. And that's how much we will use it. 3.59 is an interesting one. It says P implies Q P implies Q equivales not P or Q. Now, why in the heck, why in the heck is this the case? Well, think about it. What's the only way P implies, well, I'm sorry, I'm going back to truth tables, but
P has to be true.
yeah, the only way that this could be false, the only way that this can be false is if both of these are false, right? If both of the ors are false.
Yeah.
If both this is called disjunction. By the way, here's a little terminology. We're going to start using some more terminology. This operation is called disjunction. This is called a disjunct. And this is the other disjunct. Are you with me? So what we're saying is that the only way this can be true is if both disjuncts. No, sorry. The only way this whole thing can be false is if both disjuncts are false. If one or both are true, then it's true, right? So the only way it can be. So what's the only way it can be false? The only way it can be false is if this disjunct is false, but that means what? P would have to be true, and the only way this disjunct can be false is if Q is false, right? So the only way it can be false is if this is true and this is false. And then we know that that's how it works from the truth table. All right? But we didn't prove this.
Is that the definition then?
Yeah, I'm not sure why our author, if he,
He's an idiot.
I'm not sure why, I have never tried the system, if making that one the definition and then making that one the theorem. Maybe it's easier to prove this from that than that from this, I don't know. But clearly you only need one of them. And here's another one, 3.60 is, 3.60 is another way to get it back and forth. This one's P implies Q equivales, P and Q equivales P. P and Q equivales P. Now this is really kind of interesting, isn't it? Because this kind of has the same form as this, right? But here instead of being P or Q, it's P and Q, and instead of equivaling Q, it equivales P. Yeah? So either these are tools, 3.57, 3.59, 3.60. These are tools whereby if you need to prove something with implies, and you want to get it back to some previous ones that you already know about with conjunction or disjunction, you can use any one of these three to get it back, and then use that heuristic of manipulating the other one, and then
What? Substitute equivals for each other on the first and the third.
the first one and the third kind of look like the golden rule.
Yeah, the second terms.
Oh yeah.
If you get rid of the implies
P
completely.
or Q
Oh, I see.
equivales P.
Well, actually, haha,
So proving one of the-
actually, you know what you could do?
Proving 360 would be really, really
Easy, because you could get it from the golden rule.
Yeah.
You could start with this side, and then equivals by the golden rule.
Yeah.
You can start with this side, equivals by the golden rule. This side equals by 3.7 this, and you'd have it.
Yeah.
Or you just have
That's interesting.
Or do the whole
just say
thing. And
equivals the other side by the golden rule, which is done.
substitute.
Oh, I see. Right. Start with the whole thing, and then we just proved 3.60 from 3.57. Boy, you guys are good. No wonder there weren't any questions about the homework. I'm going to have to go through my assignment webpage now and get rid of all those hints.
Okay.
Make it a little bit more, make it a little more challenging for you. Okay, so now you keep wanting to know what. Oh my goodness.
Oh my goodness. That's on the homework.
Oh no, I thought it's 3.61, not 3.60. Okay, so contrapositive. This is contrapositive. Contrapositive says P implies Q equivals not Q implies not P. Actually, I should say something about terminology here. let me write down 3.61. 3.61 says P implies Q equivals, not Q implies, not P. And so here's some terminology. The contrapositive of P implies Q is not Q implies not P. This is what we mean by the contrapositive of P implies Q. The contrapositive of this is this. So basically, what is this 3.61 saying? It's saying that an implication is equivalent to its what? To its contrapositive. Okay? That's what it's saying in English. An implication is equivalent to its contrapositive. Now, our author doesn't make a big deal out of this next term, but you should know it because it's very common. And it's called the converse. Have you ever, in English you say blah 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 blah. Conversely, blah 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 blah. Right?
Yeah.
So but converse, just kind of colloquially in English, I mean, it's very loosey-goosey. In formal methods, the converse means something very specific. So let me write down what this is. The converse of P implies Q is Q implies P. Now let me ask you a question. Does the converse of an implication, does this 3.61 says that an implication is equivalent to its contrapositive. Is an implication equivalent to its converse? No. Correct, it is not. Okay, so let's summarize that. An implication is equivalent to its contrapositive, but it is not equivalent to its converse. Because we saw before that, if we saw before that it doesn't mean the same thing. If I win the lottery, then I'll buy a Corvette doesn't mean if I bought a Corvette, then I won the lottery. Those are two different things. They're not equivalent. But if I win the lottery, then I'll buy a Corvette, what is that equivalent to? If I what?
Don't
If I did not
win the lottery.
No.
If I did not buy a Corvette,
If I did not
win the lottery.
Yes, that's equivalent to if I did not buy the Corvette, then I did not win the lottery. Those two are equivalent. Are you with me? Is that good?
Sure.
The contrapositive of the converse is the converse of its contrapositive.
Oh, that's I never thought about that before. The contrapositive of the converse is the converse of the contrapositive?
Yeah.
I didn't even think about that before. Do you guys agree with that?
Okay, where's the practicality though?
Well, that's an interesting observation. I never thought about that before. But it makes sense, I suppose. So because if you do the converse, if you switch them and then switch them and negate them, it's the same thing as switching them and negating them and then switching them. Yeah, you're right. It is. Well, learn something new every day. Okay, but 3.61 contrapositive is one of your homework assignments.
Sweet.
All right, so you'll prove that for me. And then here, 3.62. Now this is interesting. It kind of P implies Q equivals R, that's another way to get rid of the implies, I guess, huh? It's P and Q equivals P and R. That's an interesting one because it gets rid of the implication. And 3.63 implication does distribute over equivales, right?
Wait a second.
Yeah, question?
Yeah, just wondering with 3.62 and 3.63,
Yes,
they start with the same thing,
they do.
and then it can go to two different things.
Yeah. Yeah, interesting, huh?
Very.
It starts with the, yeah, they have the same thing on the left-hand side of both 3.62 and 3.63. And 3.64 is an interesting one. Let me see. Actually, 3.63 is on your homework assignment. You're going to prove for me. 3.63. And then 3.64 has P implies parentheses, Q implies R. Now notice that it's not what is it that when you have the parentheses around the first and then the third one and then you put the parentheses around this one? Associative. So what does 3.64 say? What does it say about associativity? It says that implication is or is not associative. It's not. It's not saying if you do, you know, the parentheses around the first one, it's the same as doing the parentheses around the second pair, right? But instead, it's P implies parentheses, Q implies R, equivals P implies Q implies parentheses, P implies R. And the next one is shunting. This is another one that's going to be, that you're going to prove for next time. Here you go. This one's on the homework assignment. 3.65. You'll be proving that. Shunting. Oh, actually, now what are you going to comment? How are you going to comment about 3.64 and 3.65?
One ends with where
Yeah, and so because it's equivales, we could have done it, you know, we could have moved around because of the symmetry of equivales. We could have had them both be P implies parentheses, Q implies R. Yeah. Okay. So that's shunting. And now, now we have 3.66, P and, parentheses, P implies Q. Ooh.
what?
Yeah, what is that?
Simple. You have to prove that one?
P and, if P then Q, that makes sense, doesn't it? 3.66? I did not assign that one. But doesn't that make sense? Because if P is true and if P then Q is true,
Yeah.
then P and Q are both true. Makes sense, right? And then P and Q implies P
What?
is P regardless of whether Q is true or not.
Because P is already.
Yeah, you can kind of mentally do the truth tables for these if you'd like to see that they make sense. Of course, we're not doing proofs by truth tables anymore. And what about 3.68? If P is true or if P then Q is true, well, one of those has to be true. It's kind of like an excluded middle, isn't it?
A little bit.
Depends on what it-
And by the way, it's a little bit redundant here. Do you see that some of these are a little bit redundant because we have equivals true?
Yeah.
If we wanted to, we could have used 3.3. We could have done it in the style of the way that we did excluded middle and not put the equivals true.
Oh, true.
Are you with me? So sometimes our author puts the equivalence true there, and sometimes, just for emphasis, okay? So that's just the style. All right, and 3.69 is P or Q implies P. So notice that we have a P and P and P implies Q, a P and Q implies P, and a P or P implies Q, and a P or Q implies P. So those are all 4 possibilities. And they all turn out to be, you know, simplified. Yeah. All right. And then 3.70 is a homework problem. P or Q implies P and Q equivals P equivals Q. Ooh.
So it's true if they're the same.
Yeah, true if they're the same. Okay, so that's a homework problem. 3.71 is also a homework problem, reflexivity. I think 3 points, yeah, I always try to assign a few easy ones as well as a few challenging ones. I think 370, 371, and 372 are all pretty straightforward. Or not, 3.71 and 3.72 are pretty straightforward. Because look, I mean, how are you going to prove that P implies P equivals true? Well, just go back to, you know, go back to those definitions of implies, you know.
Why does he keep writing the equals true?
Yeah, it's just a style. Why does he keep doing, sometimes he does equivals true, sometimes not. So this is just for emphasis. Well, now this equivals true is redundant, but P implies true would be necessary. I mean, this could be stated as just P implies true. And true implies P equivals P. Oh, that's an identity.
What?
Remember what an identity is? What's the identity of multiply?
No, it's not doing
What's the identity of multiply?
1.
It's 1, because 1 times x
Yeah.
equals x. So instead of 1, if you have true implies x, what does this say you get? X. So you see, true is the identity for x. Excuse me, true is the identity for implies, but it's not, it's a left identity. It doesn't work the other way around. If you do x implies true, in fact, what do we have?
X implies true is true.
Yeah, it would have to be x if it were the right identity, but it's not. So it's possible for something to be an identity only on one side.
Goes back to you.
Oh. So put that in your pipe and smoke it. All right. So I didn't assign the left identity of true. And then here we have P implies false equivals not P. And false implies P equivals true. I think those would be pretty easy to do.
This is due Monday.
This is due Monday, yeah. And you've got 2 more. Yeah, this is getting to be substantive. So now on 3.76, we have these weakening, strengthening ones. Okay, so let's see how weakening, strengthening works. We've got, the first one is P implies P or Q. So 3.76a. Actually, 3.76a, you're going to prove it. It's P implies
You can keep going if you want.
P or Q. We can keep going.
Yeah, we can prove this one.
Oh, we can, well, I'll let you prove it.
Oh, thank you.
Okay, so it's P implies P or Q. Now, does this kind of like make logical sense?
Sure.
Because what this is saying is that if P is true, then P or Q is true.
Because P is true.
Yeah, well, if P is true, then P or Q is true,
Yeah.
right?
Yeah.
I mean, it makes sense because
P is.
if P is true, then of course P or Q is true. It doesn't even matter what Q is.
Yeah.
Now look what this says you can do. This is quite remarkable. What this says is that anytime you have a P or Q it follows from one of them
Yeah.
going the other way.
I get it.
Right? Now that's called weakening the consequent. Now actually, here's some more terminology. Suppose we say P implies Q. Now, we're going to use this terminology a lot. We just learned the terminology of a conjunct and a disjunct. Well, this is an implication, okay? The left side of an implication is called the antecedent. Are you familiar with the English word antecedent?
No.
It's something that comes before.
Okay.
All right? Like, the antecedent event is the one that came before the other one. Antecedent to having an accident, the brakes went out. That was an antecedent event. Okay? So that's the antecedent. The one on the right-hand side is called the consequent.
Can you substitute consequence for consequence? Like equals for equals?
Wait, what?
Oh, actually, we are going to have a proof technique that allows us to use the implication where we are now using equals on the left-hand side. But we're going to get to that later. The answer is you can't quite, well,
Well, you can.
you can only substitute equals for equals. You can't substitute something for something.
No, like
Can we
consequence.
substitute consequence for consequence?
Yeah.
We have P, can we change the Q to something else in one of our proofs?
Yeah, like you can change.
Well, we are always using, hold on, when you do these proofs with implications, we are still using the same three, we're still using the same three principles. And here they are. Look. Here they are.
Okay.
We are still using Leibniz to substitute equals for equals when we go from one line to the next. And we are using substitution whenever we want to get a previously proved theorem into a form that we can use. And we are using transitivity because when we have this string of equals, if this one equals this and this one equals this, then the first one equals the last one. All right? So we're still doing these three things, and we have to do those three things still, even when we're doing with these.
Okay.
Are you with me?
Yeah.
All right. Okay, so that's 3.76. Now, so now do you see why this is called weakening the consequent?
Yeah.
Because this is the consequent, right? And it's weaker. The consequence is weaker.
What do you mean by weak?
Yeah, that's a good question. What do I mean by weaker?
It's more diluted.
Yeah, it's more diluted. Okay, look at it this way. It's true in more states
True in all states.
than this one. It's true in more states because there's an or Q there, right? So it's weak. It's not, I mean, it's true here, it's true there.
It doesn't mean a lot.
Whereas look at B. Look at B. B, it's P and Q.
Which is true in one state.
P and Q implies P, right? So this is called strengthening the antecedent. So this is the antecedent, right? So what this is saying, well, but not, look, this is a whole lot stronger. This is a whole lot stronger than this. Why is it stronger? You're saying more because here you are saying that P is true and Q is true. Here you're just saying P is true. So this isn't true in as many states. It's tighter. It's only true in, it's more limited. So it's stronger. It's not true. It's true in fewer states. Do you see what I mean?
Yeah. Still don't understand why you can't substitute consequence with consequence. Like, wouldn't the same...
Well, what do you mean? Okay, give me an example of
Like,
what.
if you have P implies Q, could you say,
That same
Okay,
P-
suppose you say P implies Q, and you want to say equals, and you're going to do something, blah, blah, blah.
Can you say-
What are you going to want to do?
Because-
say,
of
I want to weaken
3.76,
it and make P implies P or Q.
because of 3.76.
No, not.
That same P implies,
Oh, hold it. So what you want to do is you want to go from here to what?
say P implies P or Q.
No,
Why not?
because they're not
It's
equal.
that same P though.
No. But but in order to have this, in order to have this work, this is incorrect. In order to have it work,
Oh.
you would have to have Q equivales P or Q
Yeah.
to substitute equals for equals. But Q does not equivalent P or Q. That was a good try. But okay, here.
More than one thing.
It was a good try, but you know, that's not the case,
All of it.
right?
What if that's true?
Well, but it's not. But if it were, you could substitute equals for equals. Anything that's equivalent, you can substitute equal.
It might be true in one case, but it's not valid.
Yeah, it's not true in all states. It has to be valid.
Bringing the definitions on it.
Oh, okay. So now, and then 3.77 is modus ponens, and this is 3.77.
What
Modus
does that
ponens.
even mean?
Modus ponens.
We came up with that.
Guys,
It's Latin.
sounds British.
It sounds British. Well, British is
You know
a
what
Latin
Latin's
language.
for?
English is a Latin language. What's that?
You know what it's Latin for?
You know, I don't. Does somebody have a computer? You want to Google modus ponens?
That proves.
And actually, this modus ponens is, if we were using a different kind of logic, you know, I said that the logic that's used for these formal methods is kind of a new deal. And some systems of logic are based on modus ponens instead of being based on equivals, instead of being based on equals. All right? So in some logics, modus ponens is the way you prove stuff. And what does modus ponens say? It says that if P is true and if P implies Q is true, that implies that Q is true.
It means for the way that affirms by affirming.
Is that what it says? For the way that affirms by affirming. Gee, that seems kind of circular.
Well, this true.
Oh, that's a good one.
Why exactly are we doing the new form of logic versus the...
Because the reason we're doing this form of logic compared to the older traditional way is because this has direct application to computing. That's why. This fits, the way we're doing it fits the way it fits the application to computing, to computers.
It's better than the old system does?
Well, it's a closer fit.
Right.
Yeah. And we can apply this style of reasoning to programs, and we can also apply it to digital circuitry. So this is the heart of, yeah. That's why the people who came up with this new logic were computer scientists. They weren't mathematicians.
Right.
Well, they were mathematicians.
Explains all the extra
but-
equivals true to the end.
Yeah, I mean, they were mathematicians too, because computer science is really applied mathematics. It's applied logic, you know. So they came up with this system to be a better fit for computing,
Right.
and it's still relatively new.
How new?
And then, actually, I remember. Well, I have a little story about that. I can remember. Okay, so I can remember when I first saw this system. And a guy by the name of Dijkstra, Dijkstra, he's Dutch. He was Dutch. He passed away not too long ago, just a few years ago. Edsker Dijkstra. It's D-I-J-K, but it's pronounced Dijkstra. So it's Edsker Dijkstra. He gave a seminar at UCLA, And I went to the seminar, and it was about this new system of logic, and he actually did these theorems that we're doing now. And that was the first time I had ever seen it. And he was showing how, and he was asking, he was getting participation from all these computer science, students and professors and stuff.
Wait, when was it?
And this was, well, it's in my lifetime. Let me see, I've been here for 35 years, so it was probably maybe 20 years ago, 25, something like that.
It's old in my book.
So, well, it's old in your book, but what about Newton? I mean, look, Newton was the father of physics, right? He was like, what, 1600s? I think, wasn't he, 1600s?
It's kind of old.
And so physics, I mean, computer science is very, very young compared to physics and chemistry and even biology. Astronomy, yeah. Astronomy is probably one of the oldest. Yeah. Okay, anyway. So a lot of these ideas are still fluid and, astrology. And then modus tollens is not in our book. But I actually had a student here last year who had some logic in his philosophy classes, and he knew about modus tollens. And so I said, oh, you're right. We don't have modus tollens on there. And so modus tollens is P implies Q and not Q implies not P. And so I had to prove this. I had to prove it from what went before to make sure that I could stick it there, And sure enough, you can.
I like the translation of modus tollens.
Oh, do you have a translation for modus tollens?
The way that denies by denying.
The way that denies by denying. And the modus ponens was the way to affirm, that affirms by affirming. Yeah. Oh, that's good. I didn't know that. All right. And then we have these others. Here's mutual implication. Does this make sense? I think we've seen this before. Mutual implication says P implies Q and Q implies P equivals what?
P.
P equivals Q. But didn't we see this
We were doing that with
and with the words? We said if and only if. We said if, blah, and then if and only if. So if and only if is P implies Q, and P, and then we said that was equivalent to equivals. So that's a theorem. You can prove it. And here we have some transitivity theorems. P implies Q and Q implies R implies P implies R. Make sense?
Yeah.
If P implies Q and Q implies R, then what do you have? P implies R. Right?
What's the difference between mutual implication and antisymmetry?
They're all the same.
No. They're not the same thing.
Oh, wasn't the first? Oh, okay.
This is P implies Q and Q implies P. So this is one way and the other way. But this one is P implies Q.
And Q.
Oh, you're right.
It implies.
One equivales.
But one equivales and the other one implies.
Yeah.
Yeah.
It can do two different things.
Yeah.
Nifty.
Actually, this is related to strengthening, I think. If you think about it.
So,
Well, if it equivals, doesn't that imply that it implies and it follows from? So it's kind of redundant.
Yeah.
Yeah, it's related that way. Do we have time to do a proof?
40 seconds?
40 seconds?
Quick proof.
You want to do a quick proof, or shall we end early?
40-second proof.
How about proof of 3.62? It's a short one. P implies Q equivals R. Here, let's do 3.62. Which is 3.62 is P implies Q equivals R. Q equivals R. Equivals P and Q equals P and R. Equivals P and Q equals P and R. So here's the proof.
One side to the other.
One side to the other. P implies Q equivals R. Equals by, we're going to use 3.60. with Q replaced by Q equals R? What do you think?
Yeah.
Do we have 360 up there?
Yeah.
Okay, so so what's this going to be?
P and Q equals R equals P.
P and Q equals R equals P and Q equals R equals P
You can distribute.
by what? So now what?
Distribution of
3.40,
who cares? The distribution of and of equals.
3.49.
And over.
Here we have a P and Q equals R, right?
Yeah.
So what does it say? 3.49 says
Isn't
what?
the distribution of and of equals?
We never had that one. Oh, we did. Can you go back one more?
Yeah, go back.
Yeah.
Pretty sure there is.
What, you mean come back here?
No, we never had and over equals.
Oh,
No, yeah, actually it does not.
right.
And does not distribute over equals. Yeah. So this is by 3.49. What?
P and Q equals P and R
Huh.
equals P.
Wait, that would be
No,
distribution.
no. We've got the equals P here.
Wait, isn't that distribution?
Wait. We've got the
Oh,
equals.
so you-
We've got.
yeah.
So boom.
Yeah.
Yeah.
Wait.
See you next time.
You use symmetry to flip 49 around so that P and Q equals P equals P. Yeah. Yeah.
You just tossed out the peas.
No. We used this P
As a part of
as part of the
3.49. If you put the P before everything.
right. Do you see that?
No, I don't.
See, look, this P is part of 3.49. 3.49, it's this P.
Oh, right.
This,
right,
it's
right.
this,
Yeah.
equals this, equals this.
Got it.
All right.
There you go.
Oh, you got homeworks. Good deal.
You already done your sign off?
Oh, did I not do the sign off already?
Do you want to do one?
So, see you next time.